Next topic is fast Fourier transform. Fast Fourier transform is an algorithm to make the DFT fast and efficient. To use the FFT, the number of samples should be always a power of 2. Means that the power of 2 means 2 data length should be 2 over 4, 8, 16, something like that. So any 2 to the n power. Okay, if data length is not fit this the power of 2, then we need to use zero padding to make it length becomes the 2 to the n. So anyway, we can using the fast Fourier transform by use of zero padding. The number of data at here, the n is always power of 2. Power of some 2 to the power of something. So n will have 2, 4, 8, 16, 32, something like that. So this kind of number. What is the property of this kind of number? We can dividing n over 2 and do again n over 4, and final, if n is a power of 2, then final will be n over 2 to the something will becomes 2. So final, it will reach to the 2 pair like that. You can keep in mind that the data is a power of 2. The number of data is a power of 2. So here shows that the DFT definition is xn is a multiplied basis function of wn, and nk is multiplied and n changing from 0 to the n minus 1. So this is n data. But n is a power of 2. Then we can separate the xn with the even order and the odd one. So even sample and odd sample are separated. And then w of n can be, n is even, but in this case n is odd. Okay, by multiplying this one. So you can see this one is w n k times 2n plus 1. So this is n is odd case, but this one is n is even case. But 1 will come out here and the 2m is over here. Then you can see that we multiplied the same basis function on here. But the issue is this one. What is the value w n over 2m is the same as w n over 2 to the m. You can see by definition is e to the minus j 2 pi over n times 2m. But the same thing can be interpreted in this way, e to the minus j 2 pi over n divided by 2 m. So this one says this one, but this one is this one. So it's the same thing. Okay, so we can change this number as this way. This one is even number. Okay, we can reduce the basis function as a half of the original one, and this one is multiplied over here, and the summation applied over here. Then that will be given. Then we define this one as a AK. So you can see this one is the DFT of half size of them. Means that the number of data is n over 2. So half size of the DFT. This one is another half size DFT for the other sample. This one is even sample. Even sample DFT is expressed by AK. Other sample DFT is expressed by BK. So AK plus WN K BK is the XK. K's DFT value can be expressed in this way. But what about this one? K plus n over 2. We added n over 2. Then you can see here that the n over 2 is this one. If you refer here, obviously this is 1. So you can think about that this is 1. What about this one? If you apply the same thing over here, that is minus 1, because if this is n and if you apply n over 2, that becomes the e to the j pi. So j is omitted here. Okay, so if we replace the k with the k plus n over 2, so k is replaced by k plus n over 2, then w of n over 2 is the same. So you can see it's the same because this is 1 and this is the same thing. So when we calculate this one, ak is the same and bk is also the same. So even though this says that the ak plus n over 2 should be equals to ak. So we just replace the k with the k plus n over 2. It doesn't change this basis. But this one will be changed at the signs. Okay, that is minus. So compare the xk and xk plus 1.5. So when we calculating xk, we can find out in this way. What about this one? That can be given in this way. It's quite easy to calculate these two things by use the same result. ak and ak is the same. bk and bk is the same. That's defined over here. So this structure is repeated at every steps. So look at here that this is ak and bk. Then by summing up ak and plus bk times wk over kn, and that sum will be xk. That's this one. So ak plus wnk and bk is the xak. But what about this one? That is ak. That's this one. So ak is provided here, and bk is multiplied this weighting factor wnk and subtracted it at here. That becomes xk plus n. This is called the multiply cell diagram of the FFT. That can be expressed over here that here is the 8 sample number is a, n is 8. In that case, we can apply the same idea from here that the x0 and x4 is applied to the multiply cell. Then this becomes the n equal 2's case. So 2, 6, 1, 5, and 3, 7. That is the multiply cell, and that is applied the next multiply cell. So this one multiplied here, that becomes the n equal 4 cases. And the last one is 8 cases. We can find out the DFT by use of this method. The same diagram can be redrawn in this way. So this is the data is ordered, but the spectral domain is reordering is required. But the previous one, the spectrum is ordered way, but the input data is reordered. It should be. So if you apply these multiply cell and its data, you can find out the spectral domain very efficiently. And also, this one is very fast. You know that these functions, so that's this part. This can be pre-computed. If n is fixed, then this is pre-computed values. So we do not waste any times to calculate this one. Just the multiply cell is repeated. It looks like a recursive structure. So it's a quite efficient and fast algorithms. So when we calculating Fourier transform, we always using the FFT algorithms. As we shown here that we are using the FFT, but the number of sample is not always 2 to the n. In that case, we can add zeros. Okay, it doesn't affecting any changes in the spectral domain by adding the zero padding. So we talk about from DFT and how the DFT show up and how to make it faster by use of FFT algorithms. That's it.